Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 4.2, Transformation or Mapping with Matrices. So there are quite a lot to go through today. We need to learn how to do reflection, rotation, stretching and shearing on a 2D dimension graph. And I'm going to talk about each of them separately just to make sure you understand what you're doing. And on a side note, you will be expected to know a combination matrix of the transformations, which I will again explain. So starting off with this set equation, well, not equation but matrix, let's try to use this to transform or map a certain vector. So we've done vectors before. In the 2D form, we have a general form xy as your general equation. Then you've got a matrix. So as I have taught you last time, as long as the dimensions, the middle term of the dimensions fits, then it can be multiplied. So let's try seeing that. This is a 2 by 2, this is a 2 by 1. And indeed, the middle terms do match, so we can do a multiplication. If we do a multiplication, then we get 1 times x plus 0 times y give us just x. 0 times x plus minus 1 times y give us minus y. So in this case, we have somehow transformed xy into x minus y. This corresponds to a reflection of along the x-axis. So this is one of the reflections. There's another one along the y-axis. You can prove this by doing exactly the same thing, but I will tell you that it's minus 1, 0, 0, 1. What about along xy? Well, good question. It's literally just the combination of both of them. Minus 1, 0, 0, minus 1. Then you flip along the let's see, you flip along this axis, I'm pretty sure, plus 1 minus, yeah. So rather, if you have a x value of say 1, then y value of minus 1, you end up with a, actually no, this is not quite. It would have to be, well, if we do reflection along these lines, then you would have to do the algebra to formulate. So let's say A, B, C, D as your transformation matrix. You've got a point x, y. It will equal to, let's see, if I reflect over this line, then right, I'm gonna leave you hanging here actually, because this is some other topic that I'm gonna talk about in the future, and I'm not gonna spoil it just yet. It's called invariance. I'm gonna tell you the name of invariance, and you can either look it up, wait for my video, or just ignore it for now. But let's hop on to rotation after we've done the simple reflections. So right here we have a very typical rotation matrix. This is general form. I don't think you're supposed to know the general form, because the most you will transform is just right angle transformations. So either 90 degrees, 180, or 270. Of course, when you say 270, it's 90 degree in the opposite direction. So again, rotation matrix, make sure you state where your origin is and what angle your transformation is, clockwise or anti-clockwise. So to be honest, nothing much to talk about here. Let's find the matrix for a anti-clockwise 90 degree rotation. So that would be anti-clockwise, by definition, is like, well, by definition an angle is positive in the anti-clockwise direction. So let's just put 90 degree on theta. Cos 90 is 0. Sine 90 is 1. Sine 90 is 1. Cos 90 is 0. This should be a rotation matrix anti-clockwise. Let's try that. So if we have x and y, then we multiply to minus y and x. And on a Cartesian graph, xy general, and after we rotate anti-clockwise, we should have a minus y and a positive x. Yeah, this should be the point, and indeed x is minus y, y is x. So yes, this is indeed anti-clockwise rotation. You can fit in any theta values to get any angle transformations. This is general form, it works. There's a 3D variant, but it's out of spec. I'm not gonna torture you through that as well. But yeah, this is rotation. Let's move on to stretching. So a stretching matrix general form is just A 0, 0, B. You would see this similar to the identity matrix 1, 0, 0, 1. They do look similar, except they have different numbers in it. And if you stretch a certain direction by a factor of 2, in this case this will be the x variant. Stretching the x value by 2 means that essentially if you have a unit square, you would get a rectangle instead. So rather than having a unit 1 on the x, you have 2 on the x. But anything else is identical, it doesn't change. But bear in mind you also have another stretch factor of 3 on the y direction, so you actually have a 3 on the y-axis. So instead of a unit square, if you transform a unit square by 2003, you get a rectangle with height 3 and width 2. Yeah, nothing much else to say, to be honest, for stretching. One special stretch is called the enlargement, which means that it is literally just A times the identity matrix, where A is the expansion factor from the origin. So if I have a unit square and A is, say, 2, I'll get a 2 by 2 matrix. Well, 2002, which means that I expand this unit square by a linear factor twice, area factor 4. Yeah, that is all for stretching, really. Important thing to note is that the area is the determinant of your transformation matrix, which I will again spoil, but leave the content to my next video when I talk about determinants. So stay tuned for that. And finally, something new for change. This is a new content called sharing. So old A-level doesn't have this. It's completely new as of, say, if I have, I'll do it a bit larger. If I have a unit square, 1, 1 from the origin, if I share it by a shift, right, I need to be careful of my terms there. If I share it in the X direction, I get a certain, actually I should change my color, shouldn't I? Color. I should get something along the lines of this. So this has been shared by less than 1, because if I share it by 1, then it would be a perfect diagonal, 45 degree. But anyway, the point is, when you share something, the area doesn't change, and the if you share it by X direction, Y value doesn't change. So literally it's just a shift, kind of. The perimeter, however, will increase, so bear that in mind. Let's have a look at the actual transformation. Say if I do a 1, 1, so, or actually I'll just do XY again in general form, do this share 1, 2, 0, 1. To see that it is a share matrix, you just need to again look for the identity matrix, then see if the zeros have changed values. If they have, congrats, it's a share matrix. So let's see this. X plus 2y, and this will be just y. So as you can see, y value doesn't change. X was changed by adding 2y, and 2y in this case would, as you go up, it will go twice further. So a more accurate version of this would more like would look a bit more like this. This would be the after share, this would be the before share. Again, I need to talk about something new. This is called the share factor. So share factor, it's a strange little something, because it comes down to combining different shares over and over again. So if I share this square once and it gets to here, if I then share it yet again, what would you expect it to do? Well, for me, logically speaking, I would expect it to share again over something like that, and indeed it is what should happen. In matrix form, when you combine two transformations, you multiply the matrix together. The later transformation on the left, the older transformation, or the first. So after you apply your transformation and you want to apply another one on top of it, you do it on the left. So let's try to share this matrix twice, by this matrix twice. So 1, 2, 0, 1, 1, 2, 0, 1. multiply this, we get 1. Then this would be a 2 plus 2 is 4. This is a 0. This is a 1. So now this one looks kind of, you can't extract much information out of this, but if you keep doing it, if you have 3 of them, you get 1 6 0 1, 4 of them 1 8 0 1. Then if you do n of them, you start to see a trend to get 1 to n 0 1, where this is 1 2 0 1 to the power n. So 1 2 0 1 to the power n gives 1 to n 0 1. And this is true for all shear matrix. So and so this 2 is the shear factor, and the number of times you apply this shear matrix is n. And this is just something that can help you shear in consecutive times. Say if I want to share something by a certain matrix 5 times, then the exam board wouldn't actually expect you to actually multiply 5 2x2 matrices, because that's just tedious and boring. They would expect you to use this shear factor method. And yeah, that concludes sharing. Yeah, one side thing to note, you could be expected to conjugate a rotational matrix with a reflection matrix, and you are also, well, any combinations, again, it's just multiplying two matrices. So if I have 0 minus 1 1 0, this is a rotational matrix by 90 degree, and if I want to also stretch it, then I can do a 3 0 0 4, and if I multiply that out, then I get a 0 minus 4 3 0. This matrix will rotate it the object by 90 degree in the positive direction, aka the anti-clockwise direction, as well as stretch. Actually, it would stretch in the x direction first, and stretch in the y direction by 4. So x by 3, y by 4, then rotate. If we flip these two, you get something different, because rotation after stretching is different from stretching before rotation. Something to bear in mind. The tips. It's kind of obvious to do these kind of matrix rotations. You either are given a mapping matrix in a certain form, or you are expected to share something or rotate something by something. If you know the matrix, then you can do it. If you do not know the matrix, you can also use algebra. Just do a simultaneous equation to find out. Just plug in the unit square and try to do algebra. Really, you can always formulate your matrix, especially for these simple matrices. One thing to note, sharing is new to this A-Level 2019 exam variant. I'm pretty sure they will throw at least a question on sharing for their first paper. Do take note. Know how to do sharing. know your shear factors, then you should be okay. Also, combining transformation and matrices, do them in the correct order. I've seen a lot of people just like completely messed up the order of matrix multiplication. They're not commutative. You cannot do them in the wrong order. So yeah, that's all tips for this video. So I want you to write down the matrix such that well, it fits the description in the following. And yeah, you have again 5 seconds to pause the video, do the questions, then I will show you the answers in 5, 4, 3, 2, 1. So the answers are shown right here. It's relatively straightforward. Question 3, make sure you do the transformations in the correct order, then you should get this. Anyway, this would be the end of this video. I hope you've learned something, and if you have any questions, leave it in the comment section below, and I will see you on my next one.